Okay, so for the final story, I want to talk about something where we've taken catalysts out of the lab, out of the test tube, if you like, and are starting to use them in new environments. And the new environment we're going to use them in are materials, in particular composite materials. So composite materials are materials made of two distinct, different components that when we put them together in one material, give us properties which are unlike the two constituent parts. Something like steel reinforced concrete would be a composite material. Or in fact, the type of composites that we're interested in are carbon fibre reinforced polymer materials. So basically plastics that are stiffened with carbon fibres. These are fantastic materials, replacing a lot of traditional materials. It's maybe the best thing to do here is to show you something that's made out of a carbon fibre reinforced composite. So this is made out of carbon fibre reinforced composite. This is a car door from a Mercedes concept sports car. Now I've never picked up a regular car door before, but I think even with my men's strength, it would be, it'd be pretty difficult to do something like that with a car door. This thing is incredibly stiff, incredibly strong, just as strong as a regular car door. But it's incredibly light. In fact, this thing is so light that even a 3-year-old can pick it up. So these materials are extremely strong but extremely light. And materials which are extremely strong but extremely light are perfect for aerospace applications. And these are starting to replace more traditional aerospace materials like aluminium, for instance. So here we have the Boeing Dreamliner. This plane basically has plastic wings. This has got carbon fibre reinforced polymer wings. It's not just civilian aircraft, it's military aircraft. The Airbus A400M wings of this are actually made just up the road in Filton. Again, this plane has plastic wings. And it's not just aeroplane. I mean, aerospace applications cover things like wind turbines as well. Wind turbine blades are now being made of carbon fibre reinforced composites. So fantastic materials, but they have their own problems. A particular problem with carbon fibre reinforced composites is that if they get damaged, it can be very difficult to detect that damage, and it can be difficult to repair that damage. To give you an example, I've got a small piece of a composite here, and this is pretty small, but this is basically been smacked with a hammer. And there's a small dent in it. You probably can't see that, so let me show you a close-up of this. So this is one face of this. It's got a bit of a dent in it. And if you've got a dent like this in your car, you'd be annoyed, but you'd probably not bother with the insurance to get this repaired. However, if you look at the other side of this panel, this barely visible damage on one side has caused complete delamination on the other side. This is catastrophic failure. You couldn't use this as a structural component. And you can imagine if we're having applications like aeroplane wings, it's pretty important that we don't get barely visible damage, which could lead to catastrophic failure. And for that reason, composite aeroplane wings have to have very strict inspection regimes. People have to look very carefully at these things, and if they do see any damage, the repair is often as crude as just gluing another piece of composite on top or bolting it on top. And of course these things are getting damaged all the time. Debris from runways, bird strike, people in workshops dropping spanners on it. So there must be a better way to do this. And we took inspiration from the human body. And the human body hasn't evolved that it can withstand any damage. If we'd evolved like that, we'd have skin as thick as a rhinoceros. And certainly if we get a small cut on our finger, we don't need to go to the doctors to get that patched up. No, the body repairs itself. We have self-healing mechanisms. The cut will bleed, it will scar, and it will heal. So why can't we have those same sorts of self-healing mechanisms in a composite material? So the concept would be something like this. Here's our composite material. And within the composite material, we've got these blue spheres here. And these are tiny little hollow spheres that we will fill with a healing agent. Now we need some sort of trigger for that healing agent. And the types of triggers we have, the things that will cause a chemical change, well, that's a catalyst. And the yellow dots here are a catalyst. So if we get a crack come in, so here's a crack in this material, and you can see what the crack will do is it now ruptures one of these tiny microcapsules. And now we've ruptured one of the microcapsules, the healing agent inside of that can leak out. So here comes the healing agent leaking out. But in leaking out, for the first time, this healing agent now comes into contact with the yellow dot, with the catalyst. And that catalyst causes a transformation of the healing agent. It causes a curing. It causes it to become solid and repair that crack. So the red line here is the repaired crack. Now, of course, this is not going to repair something if there's a huge, great hole in the wheel. But often, that's not what we need to repair. What we need to repair are very small cracks, just micro cracks, that might become bigger cracks later on. And this should be an ideal way to do that. So let me show you one of these microspheres. So I guess it looks like a distant planet or a moon or something here. But just to give you a sense of scale of how small these are, here's one of these microspheres alongside a human hair. So the band across the middle there is a human hair, and this is a microsphere in comparison. This particular microsphere is about 10 microns across. I also have some images of these things being ruptured open. So here's our microsphere. If we now burst this thing, you can see the healing agent starting to come out until eventually the microsphere is empty. It's very difficult to see what's going on in a composite material when we're healing it. We can't see through the composite material. But we can do the same sort of thing using glass slides to allow us to see what's going on. So in this video, let me show you some of the chemistry. So this is the healing agent we're using. This is what's contained within the microspheres. The catalyst is very simple here. It's based on scandium. And that catalyst causes this to form a very large network. And it's that network which glues the crack back together. So let's see that in action between two glass slides. So we put a bit of red dye in the microcapsules as well, just so you can see what's going on. We're going to add some microcapsules to one slide, then onto a second slide, and to this second slide, we're going to add a little bit of catalyst as well. So here's our scandium catalyst. And mix that together a little bit. And then what we're going to do is bring in a second slide, and you can see it's just like a dry powder. But if we crush them between two slides, the liquid interior comes out. You can see that liquid dye. If we do that with the one where we have a catalyst, you can see there's a catalyst there because when we crush it, actually we get a colour change. This particular one probably goes a purpley blue colour. So we need to press these together. We need to now leave them for a little while as well. So if we come back a bit later to the same slides, here's the one just with the liquid microcapsules. Okay, nothing's happened. The slides are not stuck together. But the one with the catalyst, the two slides are completely glued together. Can't budge them. Even if we take a blade here and try and prise them apart, we can't do it. They're stuck together. Okay, so that brings me to the end of the technical part of the lecture, but now comes the most important part, and that's thanking lots of people. I'd like to thank all of my colleagues here in the School of Chemistry. It's really a fantastic place to work. I wasn't going to pick anybody out in particular, but I did want to have a special mention for Paul Pringle, who was instrumental in me coming to Bristol in the first place. It was Paul that gave me a phone call one Friday afternoon to remind me that the deadline for applications was 9 o'clock on Monday morning. So it was rather a busy weekend a few years ago. And Paul has been a wise mentor and colleague and friend ever since. I'd also like to thank the people outside of the School of Chemistry, the collaborators. In particular, my friends in aerospace engineering, Ian Bond and Richard Trask, who are partners in the project looking at composite materials. The list here are my industrial collaborators. You can see the sponsors of the work by their logos. These industrial collaborators have not just paid the bills. You know, these are true collaborators in the sense that they've made a real technical, scientific contribution to these projects. But most important of all, I'd like to thank my research group. Although he said that you're promoted to a personal chair, in fact, there's very little that's personal about modern science, which is inevitably the effort of teamwork. And I've had a fantastic team to work with. So I'm not going to pick anybody out in particular. My apologies to those of you that I didn't manage to talk about your work today, the time didn't allow it. But really it's been a pleasure to work with all of you, to see you develop and to get to know you better. I'd also like to thank you all for coming today, particularly the students who took a bit of abuse from me today, sorry about that. But you know, really thanks for taking time out from your precious time revising to come along. Many thanks to my friends and family for making the journey, for being here, and for your support over the years, in particular Rebecca, my wife. And finally, I'd like to thank two people who unfortunately couldn't be here to see today's lecture. Don't worry, I'm not going to end on a mournful note. They can't be here because it's past their bedtime. I'm talking about my children, Francis, who made a guest appearance in the lecture, and Alistair. And I'd like to finish by dedicating today's lecture to them. Thank you.